everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, I will see the discussion of definition of terminology in the module 2, so which is the mathematical behavior of partial differential equation. So in this module, basically it focuses on what is actually PDE. So it's a partial differential equation and how it relates our error related problems with the mathematical behavior, and how do you classify so basically the partial differential equations, and which type of equations are used for what, and then after how do you use these equation to get the physics of the fluid in terms of grid and terminology. So these things actually we will be discussing, and here in the partial differential equation, so there are like basically non-linear and linear PDEs. So basic all partial differential equations are non-linear in nature. So we will actually linearize them and then solve these things. So first, so in the module, so basically we have a PDE. So the PDE and we have ODE actually. So we have equation dou u by dou x plus dou v by dou y is equal to 0. So this is a partial differential equation. So you take du by dx is equal to 0. So this is exact differential actually. So let's say you have this, you have this. Otherwise you have one more, let's say du by dx plus dv by dy is equal to 0. Okay. So here the difference between this equation 1 and equation 2 is, the equation 1, so the u is function of x comma y and v is function of x comma y. So in the 2, so u is function of x and v is function of y. That's it. Okay. So one parameter is depending upon only one independent parameter. So then it is called ODE. So next one parameter, it is depending upon two independent parameters, which is x comma y. Then that's why we call them as PDE. So that is the difference we have. So that is a different major difference between PDE and ODE. Now, so in the module 2, so we have three classifications of PDE. So one, we have elliptic. So where the discriminant, so b square minus 4ac is less than 0. Next, parabolic. So where you have b square minus 4ac is equal to 0. Next, hyperbolic. So hyperbolic where you have b square minus 4ac greater than 0. So these three are classified. So based on the second order partial differential equation, so which is a of, let's say, dou square u by dou x square plus b into dou square u by dou x dou y plus c into dou square u by dou y square is equal to 0. So this is what we have. So this equation, for this equation, so generalized equation, so we are applying the classification rule. So this is the part of a definition terminology of the module 2. So where you have to classify the partial differential equation based on the second order PDE. So this is what we have, which is a into dou square u by dou x square plus b into dou square u by dou x dou y plus c into dou square u by dou y square is equal to 0. So for this, we have taken the value of b, we have taken the value of a, we have taken the value of c. So when we apply the discriminant condition for these parameters, so elliptic and parabolic and hyperbolic natures have come. So when it is coming to elliptic, so let's say we have a question where describe the nature of elliptic equations. So when you take the elliptic equation example, so we have dou square u by dou x square plus dou square u by dou y square is equal to 0. So one of the definite terminology question is, so describe the nature of the elliptic equation. So here the basic nature of elliptic, like you can take it as Laplace. So where you have dou square u is equal to 0. So this is the basic Laplace equation. So since it is 2D, I am writing this one. So when you elaborate it, dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square is equal to 0. So this is what we have for the generalized form. Okay, since we are taking 2D, this is what we have. So when you take the values of A, so here it is 1, B is equal to 0, C is equal to 1 we have. So B square minus 4AC is equal to 0. So what happens actually? 0 square minus 4 into 1 is equal to 0. So what happens? So the value is minus 4. So which has come? The discriminant value less than 0. So this has come as elliptic. When we say this as elliptic, so the elliptic problems, so they are having a speed of sound which is indeterminate. Basically, when you take the Mach number, so m is equal to v by a, so where v is the velocity of the object, so a is the speed of the sound. So where a, what we take actually, so the value of a will vary, depends on the medium. So in the solid it is different, in the fluid or liquid the speed of sound is different, in the gas, let's say you can take any vacuum kind of thing, so the speed of sound is different actually. So the a value depends on the fluid medium. Now in the case of elliptic equation, I am taking an example of Mach number, where the sound waves, like, or the disturbance, I'm talking about disturbance. So when you make a disturbance, so it will actually propagate in infinite way. So like if you take a domain, so let us take this as a domain. So if you disturb a point here, so this disturbance is propagated throughout the domain at a finite speed, or at let's say higher speed actually. So this disturbance is occurred at all the points in the domain. Okay, so this is which is coming under the elliptic form. Okay, so where you can say that if you disturb a point in the domain, so it will affect the throughout the domain. So the domain of dependence and the range of influence are very high in the case of elliptic. Okay, so when you take the parabolic, so in the parabolic, so let's take dou t by dou t is equal to alpha dou square t by dou x square. So this is an equation. Let us take this is an equation where, so this is called 1D unsteady heat conduction, or let's heat diffusion equation. For this 1D unsteady heat diffusion equation, so we are basically what we are seeing. We are seeing whether this is parabolic or hyperbolic. So here the A value is 1, B value is 0, C value is 0. Because you don't have any other second order derivative except dou square t by dou x square. So sorry, A value is alpha. Okay. So with this, we can see that it is B square minus 4 into A into C. So which has come B as 0 minus 4, A has come as alpha, C has come as 0. So A has, so therefore what happens? It is 0. So this equation now it is parabolic in nature. Now basically what does the parabolic nature significant? The significance of the parabolic nature is where the temperature T is function of basically the space coordinate and the time coordinate. So the initialization is very, very important in the case of parabolic problem. It's called actually initial value problem. So for the parabolic problems, so basically they are initial value problem, and the elliptic nature when we take, they are basically called the boundary value problem. Okay, so we have initial value problem and we have boundary value problem. So therefore elliptic nature is a boundary value problem, and parabolic is an initial value problem. Okay, so as the time progresses, let us take this one as a rod, so which has a length L. So where you have at station A and this is station B. So what is the value of T at any section you take? So what is happening as with respect to conditions, temperature at A, temperature at B, the heat flows will happen, and how does the temperature varies? So with respect to this equation, with respect to the x and t, so we will get to know. So that's why the initial values at this point and with respect to time are required for this kind of problem. Okay, so this is coming under parabolic. The last one, what we see is the hyperbolic one. So in the hyperbolic one, so we have a wave. So dou square u by dou, let's say x square, sorry, only wave equation as c into dou square u by dou x square is equal to 0. So this is equation which we have. So here what happens actually, b value is 0, a value is 1, c value is minus c actually. So therefore what happens? So b square minus 4 into a into c. So which is 0 minus 4 into 1 into minus c. So which has come as plus 4c. Okay. So therefore this hyperbolic nature, so where you can see that roots are real and basically you can take it as unequal. So the disturbance is propagated in certain region actually, finite region. So let's take this is a x and t coordinate. So the disturbance is propagated, let's say, in this certain zone. So out of this box or out of this zone, the disturbance propagation, let's say, that is called zone of silence. So here it is, you have zone of influence. So this point, whatever we have, it is affecting this one. So this point cannot affect this one. Okay. So this one cannot, this point cannot affect this one. So the range of influence and the domain of dependence for the hyperbolic problem is limited actually. And so the basic example of the hyperbolic case is like you can take the supersonic flows. Okay, so where you have a shock, so across the shock, so you have flow, like flow behavior changes. So shock is a thin, very strong layer, so which actually changes the flow abruptly from one point to other point, and suddenly there is a rise in pressure, suddenly there is a rise in temperature, suddenly there is a rise in density. So these things will happen, so because of shock. So at the shock, inside the shock, whatever happens, so it will affect the flow downstream, so not about the upstream actually. So whatever the downstream it is affecting, so it is there. So whatever the points which we have in the shock. Okay, so this actually whatever we have seen, the parabolic, hyperbolic, elliptic. So the classifying these partial differential equation, which is parabolic, hyperbolic, and elliptic, so is coming under the definition terminology of the module 2. So in that additionally, so we have types of grid. So what are the different types of grid? As a one small question in the definition terminology. So where we have two types of grid. One we have a structured grid, other one we have unstructured grid. So we'll just see basically what is structured grid and what is unstructured grid. So here we have this. So here you can see 1, here you can see 2. So basically here for the grid, so they are regular entities. So the boundaries so are regular, where the grid we call it as structure. So no two grid lines will meet each other. That is structured. In unstructured grid, so the grid lines will meet each other. So that is unstructured mesh actually. So basically, in this, so we have different shapes. So we have C grid. So we have, let's say, C grid. So we have O grid. So we have H mesh. So basically depends on the geometry. So here we have, let's say, airfoil. So here also you can take airfoil. So based on the type of the curvature or based on the type of the geometry what we have, so we can take the choice of the grid selection actually. And to capture the boundary layer, so we use the refinement of grid. So we will use more number of grid points near to the wall. So that is called grid refinement. And one important thing is that so using the structured and unstructured mesh depends on the type of geometry. If the geometry is simple, we will go for the structured mesh, and if the geometry is complex, directly we'll go for unstructured mesh. So comparing both structured and unstructured mesh, so the results at the end should not vary. So performing the mesh task will be easy when you do one of this. Okay. So with this, we have seen the basic definition terminology for the module 2. So in the next session, we will see what is the basic terminology, definition terminology for the module 3. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.